Hello, today we're continuing our A-Level Physics revision series looking at fields, and in particular we're looking at electric fields. You need to see the previous video for information on what fields are and what gravitational fields do. There is an electric field in the presence of a charged object. So if you have an object, let's say it's positively charged, then there will be a field which will act radially. Now, the direction of the field depends on what the charge is. For a gravitational field, remember, the field always acted inwards. But for an electric charge, it depends. If it's a positive charge, then the field will act outwards. But if it's a negative charge, then the field will act inwards. But it'll be one or the other, not both, as I appear to show here. On the other hand, if you have two plates, where one plate is positively charged and the other plate is negatively charged, then the field always goes from positive to negative. And that will be the electric field. And that field, as we said in the previous video, is the capability to do something. And in this case, it's the capability to act with a force on a charge. So if you were to put, let's say, a positive charge in that field, then that charge would accelerate towards the negative plate. If you were to put a negative charged particle in the field, then of course it would accelerate towards the positive plate. If you take two charges, let's call them Q1 and Q2, and they are a distance r apart, then there will be a force acting between those two charges, and that force equals Q1 times Q2, in other words the value of the two charges multiplied together, divided by 4 pi epsilon naught r squared, where r is the distance between the charges. Epsilon naught is what is called the permittivity of free space, or if you've got an actual material between the charges, it will be the permittivity of that material. But most of the time we've got either air or vacuum, and for all practical purposes they are the same. Epsilon naught has a value, it's the permittivity of free space, and that is 8.85 times 10 to the minus 12. And then the units can vary. Sometimes it's Coulomb squared per Newton per meter squared, which of course is what you need to be dimensionally consistent, because the force will be in newtons, the charge will be in coulombs, and since there's two of them it'll be Coulomb squared, and r squared will be in meters squared. So in order for this to be dimensionally consistent, epsilon naught has to be in terms of Coulomb squared per Newton per meter squared. But you will also find that described as 8.85 times 10 to the minus 12. The value is the same, but the units are farads per meter. And you'll find that when we deal with capacitance. If you look at the videos on capacitance, essentially that unit is the same as that unit. Now, what is actually happening here? Well, each of these charges has an electric field associated with it. And those electric fields will have an impact on any charged particle that may come into contact with the field. So here we have a charged particle with a field, and here's another charged particle in the presence of this one's field. And so it will have an attraction or a repulsion, depending on whether it's positive or negative, on the basis of the field generated by that charged particle. Equally, this charged particle is generating a field, and this charged particle is in that one's field. So that also experiences a force, and consequently the two experience a force as a consequence of the field of the other. And that force is given by that equation. Now, the electric field strength is given by the force per unit charge. And so E equals F over Q. And if we say that, for example, Q2 is our unit charge Q, that means that E is equal to Q1 divided by 4 pi epsilon naught r squared, because Q2 is Q and F divided by Q will give you Q1 over 4 pi epsilon naught r squared. That's the value of the electric field strength. Now we come to the concept of electric potential energy. And the electric potential energy is the work done to bring a test charge, little q, from infinity to a point r away from a main charge. So here's a main charge, which we're going to call Q1. And we have got an electron right the way out here. Where are we here? Let's call that infinity. And we're going to bring that charge to here. Now, if it's the same charge, if it's positively charged, remember that like poles repel, unlike poles attract, like charges repel, unlike charges attract. So if this is positive and the charge out here, which is little q, is also positive, then there will be a repulsive force and that will push that little q away. So if we want to bring q to here, then we're going to have to do work to overcome the repulsive force. So we're bringing little q all the way along to this point here. And when it's here, it will be r away from Q1. And the energy, the electric potential energy, to bring that to bring that charge to that point, overcoming the repulsive force, is equal to Q, which is this charge, that's Q1, times the test charge, little q, divided by 4 pi epsilon naught r. Not r squared as up here, but now just single r. And that means that when r is infinity, that is when the test charge was infinitely far away, then the potential energy, EP, is equal to 0. This is the potential energy, and that's the energy required to bring a test charge from infinity to a point r away from the main charge Q1. Now, the electric potential is the potential energy per unit charge. And that's given the term V. And we express that in volts. And that's EP, the potential energy, divided by Q. And if you take EP divided by Q, then that's simply Q1 divided by 4 pi epsilon naught R. And that, as I've said, is expressed in volts. And let's give an example of how that applies. Let's think of two plates, rather like a capacitor if you like. And we have 400 volts on that plate and 0 volts on that plate. We could achieve that by connecting it to a battery. It would have to be a pretty big battery for 400 volts, but there you are. Sorry, I've got those around the wrong way. So the positive side is here, the negative side is here. This is 400 volts because the battery is 400 volts. And there's 400 volts on that plate, 0 on that plate. And there will therefore be an electric field because this plate is positively charged, this plate is negatively charged. There is an electric field. And the voltage between the two plates, V, is 400 volts. The field strength, of course, is the same everywhere between the plates. E does not change. But the voltage is going to change because on the plate here it's 400 volts, on the plate here it's 0, and so between the plates the voltage drops. Here it's 300 volts, here it's 200 volts, here, if I drew another line, it would be 100 volts and then 0. So the voltage is falling as you go further between this plate and this plate, but the electric field remains the same. The electric field is V divided by D. That's constant. The V is changing, but so is D changing. In other words, the distance between the 400 and 0 is that full amount there. The distance between 300 and 0 is 3/4 of D. And so the E field stays the same. It's the voltage that changes. So now let's just compare and contrast gravitational and electric fields to see where they're the same and where they are different. Let's take the Earth and let's take a positive charge, Q. What do we know? Well, firstly, we know that as far as the gravitational field is concerned, it always points inwards. Whereas the field for a charge depends on whether the charge is positive or negative. For a positive charge, as we have here, it points outwards. But if it were a negative charge, then it would point inwards. You cannot shield yourself from a gravitational field. Gravitational fields apply through everything. Whereas you can shield yourself from an electric charge by using some kind of insulator, or maybe an electric screen that will divert the effect of the field. A gravitational field is not affected by anything you put between the object in the field and the mass that's attracting it. Whereas the field operating for an electric charge is certainly affected by something you put between it. For example, that's why a dielectric, which is a piece of insulating material, has a significant impact in a capacitor. Look at my video on capacitors and dielectrics to see the consequence of that. What is the impact on energy? Well, in a gravitational field, let's take two positions. This is the ground, and we're going to take a position that's a distance h above the ground. Here is an object being held above the ground a distance h. It will have potential energy equaling m, the mass of the object, times g, the gravitational attraction, times h. This is true for near Earth. It wouldn't be true if you were well away from the Earth, because little g would then have changed. But near the Earth, within the first 100 metres or so, this is not a bad approximation. The potential energy is mgh. If you then drop that body, it will accelerate towards the Earth, and just before it hits on the Earth, it will be travelling at speed v, and it will have a kinetic energy of a half mv squared. And what you can say is that half mv squared equals mgh, because the potential energy will simply have been converted into kinetic energy. The m's cancel, and so half v squared equals gh. That enables you to calculate the velocity that that object will hit the Earth. By contrast, if you have two parallel plates and they are a distance d apart, and you have a positively charged charge, a little q, that will accelerate towards the negative plate. And what we've shown is that the electric field is equal to V divided by D. That's what we showed up here. But we also know that that equals force divided by charge, because that's how we defined, let's see if we can find that. Here it is. The electric field is the force divided by charge. And here the electric field is the volts divided by distance, or the potential divided by distance. So we've got now two formulae for the electric field: V divided by D, V is volts, D is the distance between the plates, and F divided by Q, the force between the charged particles and the unit charge value. And if you multiply those out, then you can say that VQ equals FD. But what is force times distance? Force times distance is a measure of the work done, or the energy. And so now we see why VQ is a measure of energy. And to take that a little bit further, if we say that energy, I'm going to call that En to distinguish it from the field, the energy is equal to VQ, then power equals energy divided by time. And that means VQ divided by T. But what is Q over T? The amount of charge moved in a particular time is current. And that equals VI. And that's why the power in an electric circuit is equal to the voltage times the current. For both gravitational fields and electric fields, the potential energy is zero when the distance from the object or charge is infinity. And if you have, let's say, a mass of the Earth here, and on this side we're going to have a charge Q, and you have a test mass M, which you move from here to here. So that's position 1, that's a later position, position 2. And here you have a test charge, and you move it to here. So the charge moves from here to here. This is distance R2, this is distance R1, and similarly here, this is distance R1, this is distance R2. And what you can say is that the difference in potential energy between the mass at this point and the mass at that point is equal to G M M into 1 over R1 squared minus 1 over R2 squared. And here, the difference in potential energy is equal to Q1 Q2 divided by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, into, I hope I can squeeze this on so you can see it, 1 over R1 squared minus 1 over R2 squared. And you see then a similarity. The 1 over R1 squared minus 1 over R2 squared is common, and these are simply the basis of the energy either in the gravitational field or in the electric field.